The next talk is on planning tasks in power systems. It will be given by Professor Sasaki from Hiroshima University in Japan. Planning tasks are usually formulated as mixed integer optimization tasks. Dr. Sasaki will show how hub-field network can be used to solve these optimization tasks.
I would like to talk about chapter on planning tasks in power systems. The objective of this chapter is to show how the capability of hub-field neural network, that is to show how we can solve some of planning tasks in power systems by using hub-field neural network. As I will show you later, hub-field neural network is a neural network in which all neurons are connected to each other. The hub-field neural network can be used in two ways. One is as an association memory. However, there have been very few applications in power engineering field. The other is to be used as a solver of some class of optimization problems. Basically, multi-layer perceptron is a mimic of human brain, but hub-field neural network for optimization solver is just a computational tool. Let's start off by explaining typical planning tasks in power systems. First, I would like to raise generation expansion planning. Even under the regulation environment, we have to install new generation facilities one by one as long as the power demand continues to grow. And the planning is very difficult, and the time horizon of this planning extends from 5 years to 20 years. Then the fuel purchase planning is a very key point for operating power systems. And this planning problem is rather political than economical one. The third is maintenance scheduling of thermal units. This is a mostly technical problem. As you know, thermal units is operating under very critical conditions, and they will fatigue maybe in 1 year or 2 years, and so regularly we have to maintain this very delicate apparatuses. The unit commitment means unit is a thermal unit. As you know, the power demand at night and during day changes greatly, and so most of steam unit must start up in the morning and shut down in the evening. And how to schedule of this unit's work or not work is very decisive for economies of power systems. Then optimal operation of reservoirs. This includes short term, maybe short term is 1 week to 2 to 3 months, and annual means 1 year. And as you know, we have to spend much money to make up the hydro plants, but after once we construct it, the operation needs less and less money compared with the other generating equipment. And so we are very cautious to how to use the water storage very effectively. And this is again a very difficult problem. The outage work scheduling means, like other apparatuses in power systems regularly must be replaced or under maintenance. At that time, we need to outage some parts of power systems. And there are many such outage works. And so we have to adjust or schedule these outage works in month basis or annual basis. And the last two is more short-term planning problems. And one is economic operation of hydrothermal generation systems. This is from next day to 5 minutes in actual operations. As you know, hydro plant has not produced enough electricity nowadays, but its performance is very good for maintaining the good performance of electric power systems. And also, using hydro effectively cause much economy, and so economic operation is very good. It's very important technique for power system operations. And the last is the operation planning by optimum power flow. This is our power systems is based on the constant voltage. And so if some customers want to use much power, the voltage at that point decreases quite a lot. And so in a way, we have to limit some demand of customers or increases power output from other generators. Well, anyway, this is, again, very difficult problem. The most of the previous raised tasks may be formulated as one of the followings, except the last two. And the first is a mixed integer programming problem. And the second is integer programming problem. The third is 0-1 integer programming problem. I will formulate later these classes problems. So naturally, I would like to move to the classification of the optimization problems. This is ordinal optimization problems, and here the problem is minimize f of x. This is a scalar function called objective functions. And so if without any restrictions, this is not so difficult problem. But we have to constrain some conditions. Mathematically, we use subject to g of y equals 0. This is called equality constraint. And the equation 3 expresses h of y is less than or equal to 0. This is inequality constraints. And as I wrote here, vector y take real vector, or y is called continuous variables. And this class of problems can be solved very efficiently by any of conventional algorithms, that is Newton optimum power flow or Hahn-Powell or some other methods. But there is limitations that these functions must satisfy the conditions of convexities. Next, we move to mixed integer programming problem. May I assume that some of elements of vector y must take integer values. Integer value means -1, +2, or +5, or such numbers. And then to make clear the situations, we separate the variables. And so vector x means integer vector, and y is the real vector as before. And in this case, the function the same. And we call this mixed integer programming problem because mix means mixed with continuous variables. And in this case, for some type of this class of problems, we use relaxation principle, specifically called continuous relaxation. This means we tentatively assume that element of x can take continuous value or real values, or tentatively disregard this constraint. Then this problem x is regarded as same as y, and so the problem is entirely the same as the before problem. This problem. And so we can use conventional optimization algorithms, and after that we round off the obtained results of x to nearby integer values. And you should be careful that in this case the value obtained by this relaxation principle is not totally happen to be optimal, but in general not optimal. But in almost all cases for real practical systems, this process is acceptable. Then I would like to move integer programming problem. In this problem, as you know, vector y is dropped, and instead the variables are only x, which take integer values. And so the other functions are the same, and this is called integer programming problem. Typical problem in this class is a knapsack problem. Maybe you can find a good example in such textbooks. Now move further to the special case of integer programming problems. In sometimes variable, and there is a case that variable can take only 0 or 1. In this case, we denote vector z as integer vector with 0 or 1. And in this case, only the variable is included as z. And this is very easy, relatively easy to solve because z takes 0 or either 0 or 1. And we should be note that integer programming problem mentioned before can be transformed to a 0-1 integer program, but the dimensions increases drastically. Typical problem of this 0-1 IP program is TSP, that is traveling salesman's problem. And these mixed MYP, IP, or 0-1 IP problems are frequently called combinatorial optimization problems. because in different from the continuous cases, we can obtain the optimal values after checking all the combinations of integer values. For instance, if we have in this IP problem, we assume that X is composed of X1, X2, and X3, and each X take from 1 to 10, then the combination is 1,000, okay? So if the X is n vectors, then the number of combinations is 10 to the power of n, 10 to n. And so that is easily can be astronomical number. And so this class of problems is called very difficult and problems. So our objective is to show the ability of Hopwood neural nets. And so in any way, before solving the problem, we have to know about which class of problem is easier to solve by Hopwood neural net. And this is the order of increasing the difficulties. The most easiest problem is 0-1 integer programming problems. The second is integer programming problems, and the third is mixed integer programming problems. As you know, neurons is very simple. Although you are inside your brain, there are many complicated processes going on. But if we picked up only one neurons, it's a very simple element. And actually, neuron produces outputs 0 or 1. And so this is most similar to the works of neurons. And if we want to simulate continuous values by 0, 1, it's very difficult because we need to mimic its piecewise linear functions, and it again needs much more neurons. And so this is the most easiest problem to handle. This figure shows Hopwood neural network originally proposed in Hop and Tank. As you know, a neuron produces 1 or 0 as an output, and it depends on the connections before neuron is excitatory connection or inhibitory connections. If the connection is excitatory, it produces 1. If inhibitory, it produces 0 or -1. And this analog circuit embodies this idea. And this red one means non-inverting amplifier. Non-inverting means the plus minus is not changed. Okay, so if the input is plus 0.5 volts, then output is 0.5 volts. This is just produces the same magnitude. And here is a very small dot. This is according to Mill standard. And in this case, the output is make reverse their sign. And so these two amplifiers expresses one neuron. And if this neuron, red neuron, works, it shows excitatory connections. And if green neuron fires, it shows, it means that inhibitory connections. And there is a parallel circuit, R and C circuit here, and this is to give finite time constant. Without this amplifier is going up or down instantly, and the performance is not stable. And here there is a Tij code. This is a dimension of the conductance. And this current II and Ij means bias current. And Tij is connections, the output of other neurons to these neurons, and may take any values depending on the circuit. This analog circuit looks quite feasible, but actually if we want to fabricate or implement by using the amplifiers, it is almost impossible, because the problem here, if Tij is less than unity, it's okay. We use resistors. But if Tij is greater than 1 or less than -1, it is a problem, because any passive element like resistor cannot amplify the signals. So we need amplifier at this point. So not two amplifiers here. We need many places and amplifiers to amplify, to realize this value. And further big problem is the value of Tij must change from problem to problem. And so analog implementation of this circuit is a tale story. Skipping to the details, which we're showing is the energy functions in accordance associated with the Hopwood neural networks. This is called a standard energy functions, the Hopwood network with N neurons. And this is secondary order systems, and this is terms related to bias current. And this function Vi is equals Gi of Ui. Ui is the input to neurons. Vi is output. And this is 1 plus hyperbolic tangent Ui divided by 2, means sigmoid functions. And by introducing the sigmoid functions, sigmoid function is here. Look, for certain regions for U, it takes nearly 0. For a certain region, it takes nearly unity. And these regions may be indefinite, but still continuous. And in mathematical sense, it's differentiable. And former days, as a model of neurons, all the researchers use these step functions, because this like the neurons, because under some threshold, it has no output. After over some threshold, it produces 1 unit. This looks good, but doesn't work well. So the introduction of sigmoid functions, the key success of recent studies. And this function has the same characteristics. Some of you know about the transient stability analysis by Lyapunov functions, Lyapunov's method. And in that case, we must define Lyapunov functions which clearly represent the power systems. And after, if we success in deriving such energy functions or Lyapunov functions, we can check the stability regions. And this is the same style, and this means dE over dt, that is the time derivative of energy, is negative semi-definite. Negative semi-definite means, negative definite means without this equality. And dE over dt mostly negative and sometimes becomes 0. And in any way, this means that as time goes, energy will decrease gradually, or at worst, it stays and it takes the same value. This graph shows conceptually how the energy E decreases. And of course, we are handling about n-dimensional spaces, and this is only two-dimensional. And if we assume that cut the n-dimensional space by hyperplane, maybe we can have this type of curves. And this is f of z or x, okay? And the point we want to obtain is here. But no one knows. If give this form to maybe the elementary school pupil, someone must know here is a best point. But no one knows how this is the case. And the problem is we use the fact that energy E decreases as time goes. So we have to choose some initial points. If we choose A or C as the initial points, and then work the neural networks, then energy reduces gradually from, if we start from point A, then goes to gradually to A prime. And then if we start from C, the neural network goes down to C prime. And these points are called local minima. Okay, one of local minimum, or if we call them together, local minimum. And we say that to these phenomena, we say that we are trapped by local minimum, which are not desirable phenomena. And if we happen to be chose the initial point as here or around here, then the energy goes down, decreasing gradually, and then at last we come to the point B prime. This is a global minimum. And greatest problem here, no one knows this curve. And so if we imagine a very fortunate case that we are fortunate to select the initial point here, then runs, hopefully the neural networks obtain this point, but no one knows this is the best point. So we must try again and again by changing initial point, and at last we know that this is a global minimum. Now let us move to Hopfield neural network for solving 0-1 integer programming problem. We discussed a while about equality constraints. This also proposed by Hopfield and Tank. And left half is ordinary Hopfield neural networks. And this is originally proposed to solve the LP problem, but we have changed that the input-output characteristics of these green neurons to sigmoid so that it takes 0 or 1. And this is minimize the objective function f of v. And you should note that bias current is given by the partial derivatives of this v1. And this right half is neurons in pink. I call these neurons as constraint neurons. And each neuron produces output, very large output, if this inequality constraints are violated. So, and another feature I should mention that characteristics of response time of this constraint neurons must faster than this variable neurons. So the 0-1 integer problem is mathematically formulated to minimize f of v subject to HIV is greater than 0. And this is input-output characteristics of variable neurons here, this side. And the other side is given by this curve, okay? And this side is a region where the inequality constraints are satisfied. And then once it is violated, they produce output. And originally, the Hopfield gives a curve this way. This is not correct, and this is right characteristics. So we have to summarize how we can solve the combinatorial optimization problem by Hopfield neural network. For combinatorial optimization problem, there is the objective functions and some constraints. And this is a presently available most practical method for solving the combinatorial optimization problems. This is called the branch and bound method. But as I show you later, for a large-scale problem, this needs much longer time. And so sometimes for a large-scale problem, it is difficult to obtain or impossible to obtain solutions. If the problem is not big, we can obtain the solutions very straightly and good solutions. And so another way, if we, according to objective functions, we think about the energy functions for the neural networks. And energy functions to map this problem does not take a standard form. So we have to reduce to the standard form. Then we can combine or construct the Hopfield neural networks. And then initial point, and then run the point many times, and we choose minimum of E of V. That solution hopefully be the solution of this original problem. As you see this diagram, that solution but Hopfield neural network is sometimes can get the true optimal, but mostly suboptimal solutions. So we move to the planning problems in power systems. I shall introduce the maintenance scheduling of thermal units. Thermal units means steam plants. This problem may be described as to determine the maintenance scheduling of thermal units that minimizes the sum of maintenance costs and the fuel cost during a period of study while satisfying the power demand. This is a formal description of the maintenance scheduling programs. And also the maintenance scheduling problem is a good example of 0-1 IP problem because to start maintenance or not can be expressed by 0-1 values. So we have of course, one objective functions. As I said earlier, the objective function consists of maintenance cost plus fuel cost during study period. And we raised 4 constraints. Constraint 1 is the constraints on starting period of maintenance. As you will see, each steam plant is running 1 year or 2 years, and some part are fatigue, and so we must replace or check. And so the starting period is maybe automatically determined by the maintenance records or repair records. And this next constraint is concerned the spinning reserve margin. Spinning reserve means there is a possibility that large generator is out because of the sudden fault. And so in that case, we must still provide the power energy to customers. And so mostly independent power systems securing the spinning reserve as 7 or 6 or 7% of its total power generations. The constraint 3 is the constraint not to be repaired at the same sub-period. This mostly comes from the limitations of the number of work crews. And the last constraint is constraints on the order of maintenance. This is maybe mostly in the steam plant. As you know, there are 4 or 5 steam units, and so there is the order of starting the maintenance. And so we assume these 4 constraints in thermal unit maintenance scheduling. This figure shows the mapping of maintenance scheduling onto Hopfield neural nets. This shows only the part of variable neurons. In this directions, we have unit 1, unit 2, unit 3 in this order, and this is a period. Mostly we divide 1 year to 52 or 26, depending on 1 week or 2 weeks. And so the unit 1 maybe had undertaken the maintenance work 1 year or 2 years before, then they have to start in this period. And for unit 2 must start during this time, unit 3 this time, very severe. And we allocate distribute in 2-dimensionally the neurons. And here there's not clear, but this writes V sub KT means the first subscript means the unit number, the second subscript means the time period, and so VKT means a variable neuron for unit K at period T. Okay. This is a mapping of the objective functions, and this term shows the maintenance cost. This is the operational cost. And I should apologize that there is the inconsistency of using the subscript, because this W at the second subscript should be replaced by all T. And so this is for maintenance cost and operation cost. So we skip through very quickly about the mapping of the constraints. The first constraint is constraints on the starting period of maintenance. So in that way, this is a T of K means T from 1 to T period T, this particular unit must start its maintenance work. And so this means there are TK neurons, but the addition of TK neurons, the output is unity. That means only one neuron must fire, and that means a fired neuron shows the starting time of the maintenance work. And this is equality constraints that we haven't shown before. And there is two kinds of treatment of this equality constraints. One is shifting the right-hand side here and multiplying by self and adding the objective functions. This is one way or a more normal way. But that doesn't work so well, and so we enforce these equality constraints by using this inequality and this equality. Okay, this means this summation is it's greater than or equal to unity, and also this is less than unity. And so this means that it must be unit. And spinning reserve is maybe expressed at this. And we have to speak to constraint 3 and 4. So this shows our flowchart of the neural network simulator. One start, determine initial value of VI0 of variable neurons. And there is long studies about how to choose VI0. And it is established that VI0 should be around 0.5, that between 0 and 1. And if we all choose VI0 as 0.5, a neural network doesn't work. And so we add some very small values, random sample values, VI0. Then determine input voltages UI0 of variable neurons by using this. This is a reverse function, inverse functions of sigmoid functions. So according to the assumption that constraint neurons must respond very quickly compared with those variable neurons, we update all the constraint neurons at once, and then coming into this loop and choose one variable neuron randomly and then update. This equation is according to the Euler's numerical integration formula, and this is only useful in these applications. And update all constraint neurons and satisfy, if the constraint satisfied, it's coming here. If no, coming back here. And going iterating several hundred times this loop, and then coming back converge, and then if no, for converging this. Sorry, this is mistakes. This loop coming up here and go back to here. Okay, this point. And so, in a way, in my experience, out of maybe 70 or 80% cases will converge. So we move to our base case peak load curve. This from the January and December, and you know that this data is given by the per company in Northern Territory, and not so big company. And we use 20 units for must maintain, and we divided 1 year to 52 periods. And we have prepared 1,000 initial points by using random number generators. And this is a percent. And at the same time, we obtain the exact optimum solution by branch and bound method. This is 119.86 billion N. And this is the histogram that shows the distribution of the solution, 100 solutions of neural nets. And this is the best one, and the next best is around 4%. The next best is 7% or 8%. And this is a very good solution, and including this, we regard, or we say these solutions are suboptimal solutions. And if we look at this histogram, we can't have any idea how to use hopefully the neural nets. And so this is a number of trials. Okay, this is a number of trials, and this red is under 120.3 billion N, and that is including these solutions. Okay, if exclude this one, it's the blue one. This maybe this curve you should understand, interpret that probability distribution functions of our cumulative curves. And so if we limit a better solutions, there is a possibility of appearing the solutions. Okay, so this is a percent, is a probability. And so if we accept the solution of 120.3, after 10 runs, we have at least one solutions with 0.95% possibility. And if we only accept the solutions 120.2 billion N, we need 30 runs of hopefully the neural nets. Okay, of course, this depends on the probabilistic nature, because we prepared the initial values by random number generators, and maybe the first one maybe gets one, but this is a probabilistic nature of the solutions. So this is comparison of the execution time. And we prepared, this is a base case, and this is we intentionally chose very small scale problems. Units decreased to 15, and periods divided twice, and no, that's twice long, and so 26 periods per year. And this is a branch and bound method solutions, and this column shows the number of searches, and this is execution time in seconds. And we use computers, Sun Spark Station 10, 100 MIPS. And for 15 units, 26 periods problem, the number of searches only 6,331. So the solution time is only 2 seconds. On the other hand, hop-filled neural nets for 20 runs requires over 200 seconds. And this means that for small-scale problems, hop-filled neural nets cannot compete at all with the branch and bound method. But in this case, I should say that even hop-filled neural net could obtain the optimal solutions. For our base case, number of searches jumps up to 327,000, and execution time is 2,680 seconds, less than 3,600. It means one hour, and so less than maybe 40 minutes or 50 minutes. In this case, hop-filled neural net for 20 runs, okay, not 1 runs, 20 runs, needs only 1,000, a little bit longer than 1,000 seconds. And so, but we couldn't obtain the best solutions. And we also made another big problem, 30 units, 52 periods. In this case, number of searches jump up this figure, and execution time is 53,645 seconds. Just means, according to my calculations, this roughly 15 hours. Okay, so if we run hop-filled neural networks to obtain suboptimal for 20 times, the time required is roughly 30 minutes. Okay, this is the profound time ratios. We also have solved 40 units, 50 periods for large systems. Then the time ratio is over 1,000 or 10,000. And 50 units, 52 periods. The branch and bound cannot solve the problem even run after 2 months. Okay, that means it's impossible. So this is a comparison of the minimum cost, that is the scalability of the hop-filled neural nets. This is the same study case, and branch and bound method gets 52.02 billion N, and hop-filled neural nets obtain the same value, so discrepancy is 0%. And our base case, the best value from B and B method is 119.86 billion N, and the best value by hop-filled neural nets is 119.95, and the discrepancy is 0.08%, maybe allowable for long-range planning. And 30 units and 52 periods is difference is 0.25%. It still looks acceptable. And I have no data about this large one, but in any way, the scalability is not so severe, and so as a conclusion, hop-filled neural net is maybe can be used as a suboptimal solver for the combinatorial optimizations. So we have to conclude our presentations. the feasibility of the Hopwood neural network for solving planning tasks in power systems has been discussed. The second is the optimization problems are classified into several categories, and we show that 0-1 integer programming problems are most amenable to Hopwood neural nets. The third is thermal unit maintenance scheduling, formulated as 0-1 IP problem, has been solved by Hopwood neural nets successfully. The results obtained verify that Hopwood neural net is very promising for large-scale optimization problems for which the branch and bound method is powerless. Further research is ongoing towards the combined use of Hopwood neural nets and the branch and bound method to obtain optimal solutions. This means that we run 20 or 30 runs for Hopwood neural nets and then prune the extra searching space and then moving to branch and bound method. And we have got some good results in this study, and that's our talk. Thank you.